There is absolute convergence, and then there's conditional convergence. We say that a series converges absolutely if the sum of the absolute value converges. And if the sum of the absolute value converges, then the series itself converges. Now, definitions of absolute versus conditional convergence. If the sum of a sub n is absolutely convergent, if the sum of the absolute values are convergent, while it's conditionally convergent if the sum converges, but the sum of the absolute values diverges. Let's look at a couple of examples. Does this converge or diverge? Well, let's look at the nth term. The limit as n approaches infinity of n factorial divided by 2 to the n. Now we've already shown that this diverges. So this series diverges. What about this? The sum as n goes from 1 to infinity of minus 1 to the n divided by the square root of n. Well, let's look at, for an alternating series, we can see that it does converge because the limit as n approaches infinity of 1 over the square root of n is 0, and 1 over the square root of n plus 1 is less than or equal to 1 over the square root of n. For all n. So we know at minimum it converges at least conditionally. Now let's look at the sum as n goes from 1 to infinity of the absolute value of minus 1 to the n divided by the square root of n. That's the sum as n goes from 1 to infinity of 1 over the square root of n. Now, we know this diverges because the absolute value diverges, but the series itself converges. We are confident in saying this has conditional convergence. Now let's look at this function right here. There's not a nice, neat way to write this. And I'm not really sure what to do with all these n's. So let me just start by looking at the absolute value. The absolute value of minus 1 to the n plus 1 over 2 divided by 3 to the n. Okay, this is a sum as n goes from 1 to infinity of 1 over 3 to the n. Now this, I know, converges. It's a geometric series. All right, so without any further ado, I can apply the theorem that this must converge absolutely. Because the absolute value of the series converged. Now, let's look at the sum as n goes from 1 to infinity of minus 1 to the n divided by the log of n plus 1. Well, let's see if the series itself converges. Let's look at the limit as n goes to infinity of 1 over the log of n plus 1. And yes, this does equal 0. And 1 over the log of n plus 1 is less than or equal to 1 over the log of n plus 1. Let me rewrite this. The log of n plus 1 is less than or equal to the log of n plus 2. Not by much, but especially as n goes to infinity. So I know this converges. I know this, the series itself converges, but does it converge absolutely? Well, let me look at the sum as n goes from 1 to infinity of the absolute value of negative 1 to the n divided by the log of n plus 1. Okay, so this is a sum as n goes from 1 to infinity of 1 over the natural log of n plus 1. Let's see, let me write out a few terms. 1 over log of 2 plus 1 over log of 3 plus 1 over log of 4, and so on. Now, if I directly compare this to the harmonic series, I believe we will find all right, as n gets very, very large. So this function is larger than the harmonic series, and we know the harmonic series diverges, which tells me this does not converge absolutely. However, it does have conditional convergence.